Welcome back to Wood Engineering. I'm Jeff Barochko from Carleton University, and in this video we are going to be doing an example of how to check the compression parallel resistance of a glulam column. So all the data is here, but what exactly we're going to be looking at, we are given basically the column geometry, the column species, and the column grade. We have a 6-meter long column, and at the middle of that column it's laterally braced in one direction. So that means there's some beams maybe framing into this column, and those beams are preventing the column from buckling at that location, so just in the center. At the ends of the column we have pins, so the column can rotate in both directions. That probably just means we have some kind of regular bolted connection at the ends. This is the most common end condition that we see in timber members. And this column is outside or in a humid area, so it's a preservative treated, unincised, and it has a wet surface condition. We're given the governing load case, which is 65 kilonewtons, and this column supports, this load case includes dead, live, and snow loads. We need to know that because we need to know what kind of KD factor that we're going to use. And we are tasked to predict what is going to be the strength of this and whether that strength is going to be okay given the factored load that we are provided. Okay, so let's start by just drawing what this column looks like. So as we said, we have a pin end at the top, we have our column, we have a pin end at the bottom, and then in the weak axis direction, which we'll look at when I'll draw a section to show what we're talking about, but in the weak axis direction, basically we have some kind of bracing, preventing the column from buckling in that direction. And this is a 6-meter long column, so basically we have 3 meters at the top, 3,000 millimeters here, and then another 3,000 to get to the bottom. So these are going to define, of course, our lengths for buckling in 2 directions. So in the weak axis direction, our buckling length is going to be 3,000. And it turns out that our effective length is also going to be 3,000 because the K is going to equal 1 for that case. And for the strong axis direction, our effective length is going to be 6,000 because the K is also 1 for that case because it's pin-pin. So if I were to look at the cross section of this column, you know, if I'm looking at this from above, or maybe if I just look at the cut section in 3D, then it's going to look something like this. Okay, so that is the cross section, just oriented the same as I've oriented the column on the left. And here we have the bracing for the weak axis direction. And if I were to label those axes, I might call this weak axis direction Y, and I might call buckling about Y, and then I might call this direction X. But really, I'm just going to refer to these as weak axis and strong axis because I think that's probably clearer. And we also have dimensions for this, right? So this weak axis direction dimension is 130, and the strong axis one is 152. So obviously this column continues down from here. I'm just looking at the section at the restraint. I'll make these lines a little bit more obvious for the notes. Okay, so this is what's happening here. So let's get started with figuring out what those buckling lengths are. So for the weak axis, our buckling shape is going to be something like this. And so the length is 3,000, and it's the same top and bottom. If it was different top and bottom, then we should check the more slender one. And the K is going to equal 1.0 because this buckles in like just a single curve. Okay, so you can go back to the video where we talk about figuring out what the K value is, the effective buckling length factor. And that means that our LE is going to be 3000 millimeters. So this is for weak axis buckling. Then if I look at the same thing in the strong axis direction, okay, for strong axis buckling, we're basically buckling out of plane or into the plane. And this length then is 6000. My K is still going to be 1.0 because this is like a pin-pin buckling case. So you can look at the table in the appendix of the standard. You remind you what table we're talking about here. We're talking about this table here. So here you can see that both of these cases look like this third case here, where I have just like a single curvature kind of buckling. And that means that my LE is going to equal 6000 millimeters. This is for strong axis buckling. Okay, so we figured out our LE for both directions. So now let's review what are the governing equations for calculating column strength. Okay, so we have PR equals phi capital FC A K ZCG. So for lumber, it just says KZC, and for Glulam, it says KZCG and KC, which is my slenderness factor. And we can start figuring out what these are. Okay, so first of all, my FC is, right, small fc times KH, KST, KT, and which one am I missing? Size effect, no. Treatment, and KD, obviously. Okay, you'll get used to that. Okay, so let's find all these. All right, so FC we get from our table, depending on our species and grade. So our species and grade here is Douglas fir larch, 16 CE. So if I go to my table 7.3, which gives me all the strengths. Okay, and I'm talking about Douglas fir larch. I'm talking about FC, which is compression parallel resistance, and I'm talking about 16C-E grade. So my compression parallel strength is 30.2. That's my unmodified strength. So this is 30.2. Okay, my KH is going to equal 1.0 here because I don't have more than one member supporting the same load. My, well, I need at least 3 for KH. KST, I'm going to find from a table because we said this is wet condition. Okay, so we're having wet condition, unincised, but treated. So we have KSC. Oh, I have a little typo. It should be KSC, which is compression parallel to grain. And for wet surface conditions, that's 0.75. So this is not KST. That's what it is for tension, obviously, which was the previous example. This is KSC. And then this equals 0.75 from our table. KT equals equals 1.0 because we're talking about Glulam. And KD here is going to equal 1.0. Because we're dealing with dead and live loads. And we're not given any indication actually if the dead load is larger than the live load, but let's say for sake of argument that this is just a regular case where the live load is greater, so we don't have to do that interpolation. So KD equals 1.0. All right. So now I can calculate my FC, right? 30.2, I should put some units on here. This is MPa. 30.2 times 1.0 times 0.75 times 1.0 times 1.0. Now you'll notice if you go to the standard that I mixed up the order of these compared to what's in the standard. Usually KD comes first. But anyways, I'm going with the order that I had. But it doesn't matter as long as you make sure to include all of them. So this gives us 22.6, say 22.7 MPa as our reduced strength. And now we can calculate KZCG, which is our size effect factor. And you remember, this is one of the big differences between lumber and glulam designed for compression parallel. So for lumber, this value changes depending on if we're talking about strong axis buckling or weak axis buckling. So, but for glulam, there's only one factor, which makes actually this whole process a lot easier for glulam. We'll see an example for lumber when we talked about built-up column sections. So this equation is 0.68 times Z to the power of negative 0.13. You remember it's got a weird exponent because this is an empirically derived equation, and that it has to be less than or equal to 1.0, and that number is a cap. Okay, so I put 0.68. Now here's the trick. In Z, I have to remember that this is in meters cubed. So all of my numbers here have to be in meters. Otherwise, I will not get the right answer. I'll get something really weird. So this is 0.13 because it's 130 millimeters times 0.152 because it was 152 millimeters times 6 meters, which is the length of the column. And I get 0.897, which is less than 1.0, so that's okay. Okay, and then finally I need my area, which is just my cross-sectional area, 130 times 152, and I get 19,760 millimeters squared. Okay, so now I've come up with all of the parameters in this equation, except for phi. Phi is 0.8, which you just get straight out of the standard. For compression, it's different than tension, right? So I've come up with all these: phi, FC, A, KZCG, and now the hardest part is finding KC, for which I have to determine the slenderness. So this is another big difference between lumber and glulam. You remember for lumber, I check both slendernesses, but then I go through and do a whole calculation for slenderness for both the weak axis and the strong axis. In glulam, I don't have to do that. I only have to check the slenderness. I only have to find the KC for the worst case slenderness. So obviously more slender is worse because the slenderer member is more likely to buckle. So let's find the slenderness in both directions. Okay, so I will do, let's do weak axis buckling first. Okay, so weak axis, CC, I'll call that CC weak, is going to equal the length divided by the D in the direction, right, of buckling. Okay, so here, if I'm talking about the weak axis, we remember that our weak axis effective length is 3,000 millimeters. Okay, so I found that. And what is the dimension in that direction? It's the weak axis direction, so it's the 130. Okay, so we're buckling in this direction. Okay, therefore, that's the dimension that I use when I calculate the slenderness for buckling in that direction, because it's the depth of the member in the direction of buckling that affects how prone something is to buckling. Okay, so it's L equals 3,000. Sorry, LE equals 3,000. Oops. LE equals, oops. LE equals 3,000. Okay, and we're talking about this dimension, so we're talking about 130. Okay. So let's do that calculation. Sorry, 3,000. Yeah, I said 3,000, I think, right? So this equals 3,000 millimeters divided by 130 millimeters, right? So this is a dimensionless quantity, and I get 23.1. Okay, and we remember that there's a requirement that this must be less than or equal to 50. And this is not a cap. It's not if I go greater than 50, I set it to 50, which is the case for KZCG. You know, like for KZCG, if I get a value above 1, I just set it to 1 and I cap it. In this case, you're not permitted to have a design that has a CC that is greater than 50. So we're less than 50, so then, okay, we don't need to redesign this section. Okay, so then let's look at strong axis. Okay, CC strong. Now we have our 6,000 millimeters, which is the buckling length for our strong axis buckling, which is the purple one on the right. Okay, because the restraints do not prevent the column from buckling out of plane. They only prevent it from buckling in plane, right? And the dimension in the direction of that buckling, which in this case is the strong axis dimension. So this is why I like to call it strong axis buckling, weak axis buckling, because then I just use the strong axis dimension when I talk about that, like the larger cross-section dimension is the strong axis direction. And that's 152 in this case. So I'm going to put this as 152. And what I get is 39.5, which is also still less than 50, so it's okay. Now you notice here, the weak axis is not actually the axis that's more prone to buckling. So I'm talking about weak axis of the member, not which one is more prone to buckling, right? So the weak axis actually is stronger for buckling. Why? Because it's restrained. Okay, whereas the strong axis, even though it has a larger cross-section dimension in that direction, it is more prone to buckling because the buckling length is much longer. Okay, so since we're talking about Glulam, I only have to continue with the one that's worse here. So I have CC strong as the worst one. So that's the one that I'm going to use to calculate my, my KC. Now, again, that does not apply for lumber design. For lumber design, I have to go through and check both. Why? Because the KZ factor also changes based on which dimension I'm talking about, like based on which buckling direction, and the effect of that is reversed. So it's not clear, you know, before you actually do the calculation, which one is going to govern. Although in most cases, it's still going to be the slenderness that governs, but it's just not guaranteed to be the case. So I have to check both for lumber. Okay, but so since this is Glulam, let's continue and check the slenderness factor. So I can do KC. We'll recall this equation. KZCG, CC cubed, and 35 EO5. So it's the 5th percentile, Young's modulus, KSE, KT. There's a couple parameters in here that we haven't found yet. One of those is KSE and the other one is EO5. So EO5 we get, and it says in the standard, we can get that as 0.87 times E. And where do we find E? We find E from our strength table. So if I go back to that table, okay, we're talking about 16C-E again. This is our grade for Douglas fir larch. And we read down and we see modulus of elasticity E is 12,400. So here I can fit in, I can either do this calculation or I can sub it all in together. I'm just going to keep it separated for now. 12,400 MPa. Okay, and the other one that we don't have is KSE, which we're going to go to the appropriate table for Glulam service condition factors. And we see KSE, which is different than KSC. So this is an effect on the stiffness, not an effect on the strength. And we see that for wet conditions, it's 0.9. KSE equals 0.9. Okay, so now we can go ahead and fill in all these numbers. Okay. 0.8 39.47, 39.5 cubed divided by 35 times EO5, which is 0.87 times 12,400 times KSE, which we just found is 0.9 times KT is 1.0. We cannot forget this -1 that we have to flip it. We have to take the inverse. Okay, that's an easy thing to forget. And we get KC equal to 0.2138. So what's the consequence of that? That's too many significant figures. But the consequence of that is that basically I'm reducing my strength by almost 80% because of buckling. Okay, because this is going to buckle way before it crushes in compression. So that's the price I pay for having a long column. Okay, so now I can take all of those factors and I can put them back into my equation for PR. So I have 0.8. Here's my FC, big FC, which is the one with the with all the resistances. I have let me put the units in here. So this is MPa. We have 19,760, which was our area, so that's millimeters squared. And then we have our size effect factor, which is 0.897 up here. And then the last one is the slenderness factor, which we just did, 2138. So those last two are dimensionless. The other two are MPa, which is newtons per millimeter squared, and millimeters squared. So I'm going to get a number out in newtons. And then I'm going to divide that by 1,000 just in the process of doing my calculation. So I'm going to come up with 68.7 kilonewtons. Okay, so when I do that calculation, I get 68,700. But that's in newtons, so I just divide it by 1,000 to get kilonewtons. And now I can check that this is greater than my PF, which happened to be 65 kilonewtons, you know, and this comparison is done at an equivalent KD, so the KD for both is the same. And then I can say that yes, yes, the Glulam design, the Glulam column design is adequate. And that's it. All done.